Oh, hi there. Thanks so much for showing up for your math learning. It's Mr. Jennings, and we are looking at lesson 1.1, Introduction to Polynomials. We want to be able to do the following things. I really encourage you to use your learning goals here and reflect on your own learning. Okay? We want to be able to recognize polynomial functions and make connections to linear, quadratic functions that we've learned before. This is prior knowledge. In order to describe characteristics and properties of higher order polynomials as well. So here are the things that we want to be able to do. We want to understand the general form of a polynomial and really use this vocabulary of leading coefficient and degree accurately. We want to understand the end behavior of polynomials as we go off to infinity. What are they doing? Okay, they can do these things. We want to understand the number of x-intercepts that they have. So as we're graphing these polynomials, how many times are they crossing the x-axis? Understanding the symmetry of polynomials and their possible symmetries, and the idea of local maximums and minimums. Okay, something like this is a local maximum because it's a maximum over there, but the function might get bigger over here. So this is different from quadratics, which have a definite maximum or minimum. So let's get started. When we're looking at the general form of polynomial functions, we are always going to write our variables in terms of the decreasing exponents. So we put the highest exponents first and then the lower exponents at the end. So here is our x squared term, here is our x to the power 1 term, and here is our x to the 0 term. If you kept going, this wouldn't really fit our definition of polynomial anymore, the way we're doing it. This would be like a minus 1 over x to the 1 down there. You could have downstairs x's or x to the minus 1s, but we're really not thinking about that right now. Honestly, when I see that, I go ahead and multiply by my variable to move everything upstairs. Okay, so decreasing degree, okay, decreasing degree of the exponent, and this n value there, that's the one that determines the degree of the polynomial. And we're going to see each type of degree has its own special name. We'll talk about that in a second. So n is the degree, and then the first coefficient, okay, that first number that we have there really determines a lot of the behavior of the polynomial. This is our leading coefficient. And it's significant to pay attention to that one when we're looking at an exponent and a function in equation form. We're going to want to know about that. And we can infer a lot about that value from a graph as well as from a table of values. So we'll be looking at strategies to understand that over the next couple days. And then the last one, our final constant. These numbers here, these are just subscripts. They mean like an minus 1, a2, a1, and a0, just our coefficients. And we can also use a, b, c, d, e for those. But when you have one at the end of your function, which doesn't have a variable attached to it, or it's the x to the 0 term, which is just 1 for all values of x, that's our constant. Okay, so there's some vocabulary for us. Leading coefficient, constant, and the degree of the function is given there by that n value. Oh, let's keep going. So generally, here's what our functions will look like when we're degree 1, 2, 3, and 4. We're generally going to be spending time with up to quartics in this course, and in previous courses you've seen linear in grade 9 and quadratic functions in grades 10 and 11. Okay, so now we're going to go up to quartics, but we can extend our learning off to n is infinity with these ideas. Our general forms, you have y equals mx plus b, or, oh, so that's weird, y equals mx plus b, or y equals ax plus b. That's fine, where m is the slope and b is the y-intercept. And actually, when you look at the constant term here, they're, for all polynomials, giving us that y-intercept. Okay, because to find a general y-intercept for a function, like where am I crossing the y-axis, well, you just take x and you set x to be 0 at that point, and then you'll find the value of the constant there. So this is always giving us the y-intercept. And then in all of these cases, our a value is our leading coefficient, and we have the names of these functions. Linear functions, quadratic functions. Cubic functions go with degree 3 functions, and degree 4, we have quartic functions. Now, we're going to take a look at some graphs, okay? Our degree 1 functions, these are lines, and there's, an infinite number of ways we can make lines. They have no turning points. We can describe them as being symmetrical around a point, where if I rotate the line, I would get the line back. If I rotate, and actually we're symmetrical around any point. So we have point symmetry. With quadratics, they're always symmetrical around a line. So we're symmetrical both ways around the axis of symmetry, so we call that line symmetrical. And they're degree 2. We've seen this a number of times. When we get to cubic functions, like lines, are symmetrical around a point this way, where we can rotate it around a point and get symmetry. So these are point symmetrical. Okay. And they can have like more turning points than we've seen before. So you can see here, this function has one local maximum over there and one local minimum, and can have interesting properties, which we'll discuss in a moment. When we get up to quartics, we're no longer necessarily symmetrical. You'll see this one it's not symmetrical in any one mirror, but it could be. There are quartics that are symmetrical, but these are line maybe. And for degree 5, we're point maybe. And this pattern of point symmetry going with our odd degree and line symmetry going with our even degree does continue, although symmetry is no longer guaranteed after we're degree 4, or degree 4 and after. So we'll notice the degree 5 can have as many as 1, 2, 3, 4 turning points. The degree 4 can have 1, 2, 3 turning points, and we're always going to see it's 1 less than the degree of the function. Where quadratics necessarily have 1 turning point, and cubics could have 2. Okay, so now let's take a look at some of these in Desmos, and we'll play around and take a look at some different types of roots. You have access to this Desmos graph as well, so I encourage you to get in here and play around with it. Here is our function y equals x, and there's y equals negative x, and here is a transformed one, y equals 2x plus 1. Okay, so that's nothing new. Play around, change some of those values, have fun. Quadratics, well, they might look like this, transformed. There you have, this one is not factorable, so we have these ugly roots. If I change this to plus 1, now we are here factorable, and we're factorable at 1/2 and 1. So that's something that's a little different. And then here's our transform, our parent function ones. Okay. So that's all review. Play around if you'd like some review there. But when we take a look at cubics, we see a new kind of shape happening, where it approaches the x-axis and kind of skids along the x-axis for a second and then keeps going. We can, reflect that in the x-axis there, or the y-axis. It's the same, whether you reflected x or y, and we get a different looking function that starts from up high and goes down low. And then here is a transformed one, and if you notice the way this cubic has been assembled, there's a relationship with the roots that's very familiar from factored form quadratics. So when we factor a cubic, we can also solve that cubic, like what values of x will make that 0, with the same strategy that we used with quadratics. Here you will notice if x were 3 and I put 3 in there, well, there's when x is 3, the value of the function is 0, because this factor has become 0. Watch what happens if I remove that factor. We now get a quadratic, because we lowered the degree of the function, and we preserved those 2 roots. Now, I can make this a cubic again by squaring one of the roots. And we see that cubic shape again, where it comes up, goes down, comes up again. All right? And we have here what's called a double root at -2, and then a normal root at 1. Okay? Here, -2 for x would make this one 0. Right? And this type of root, it comes up, touches the x-axis, and comes back down. All right, we'll call that type of root a bounce, like it's bouncing off of the x-axis. If I flip the sign here, you'll see it's even more looking like a bounce. Like I come down, I bounce, and come up. Bounce, bounce. So we call that a bounce root. This one we'll call a cut, where this root is a standard root, and it just goes straight through. So this one here gives us a cut at 1 and a bounce at -2. Okay? And there's cubics. Okay. So another thing that you're doing as you're exploring these is you can fill in this chart here. All right, and let's talk about some of the things that go into this chart. We've noticed that f of x equals x. It looks like this. All right, and f of x equals negative x. It looks like that, and we get our charts. All right, and they go off to infinity in both directions. These are linear. These ones are quadratic. Dot, dot, dot. I've got it, Miss Metherall has it filled in for us somewhere else. Anyway, our leading coefficient here is positive and negative, and it's our end behavior that I want to talk about. So here, our end behavior with f of x equals x is when x gets very, very negative, then this is going off to negative infinity. As x gets very positive, x goes off to positive infinity. We're actually going to come back and talk about the, end behavior in just a moment, and we'll do that in another spot. But I want to highlight the wonderful work that Ms. Metherall has left for us. This is available to you in the D2L. So the end behavior here, she's describing it by quadrants. And if you take a look at, say, like the cubic ones here, this one, as x gets very negative, our y values go off to negative infinity, and as x gets very positive, the y values go up to positive infinity. So this can be described as Q3, so this is quadrant 3 down here. So we're in quadrant 3, and then we go to quadrant 1, and we kind of do this. Okay, we do that. I'm mirrored for some reason. All right, so we'll talk about that in just a moment. When we look at quartics, here, our basic quartic looks like a quadratic that you dropped on the floor. It just flattens out right around the 0, and then it accelerates much, much faster than a typical quadratic would. Let's compare that to just quadratic there. You'll see they both share the point 1, 1 and negative 1, 1, because 1 to the power 4 is the same thing as 1 to the power 2. And they share the point 0, 0. The same thing is true at 0. But the quartic is lower between those two values and then way higher outside of those two values. Okay. And then when we look at transformed quartics, we can see they can have lots of loop-de-loos. They can have as many intercepts as they have degree. So we see there intercepts that correspond to each one of these factors. All right. So let's say we're interested in this 2x minus 1 factor. If I remove this one, the x plus 1, we're cubic now. But then I go ahead and I square that one. And the 2x minus 1 corresponds to that root where x is 1/2 and the y value is 0. Now that root became a bounce because it's a square. So it creates this bounce root. We have a cut at -3, a cut at 2, and a bounce at 1/2. Now, let's say I remove this -3 root. Okay, we're now cubic again, but then I go ahead and raise the degree of that factor to a cube. And now we have a third type of root where as the function approaches the root, it drags across the x-axis before continuing down and then coming through this cut here at 2. Yeah, so there's 2. So now we changed this root to a drag. So we'll have 3 different types of roots that we'll talk about: a cut, a drag, and a bounce. So let's create a sextic. So we are here, let's do, we'll turn this off, and we'll put our roots at 1, 2, 3, 4, 5, and 6. X minus 1 times x minus 2, put that in brackets. Let's copy it. Times x minus 3 times x minus 4. So we're now here quartic, and we see that quartic shape. We're symmetrical. X minus 5 there were quintic, and we're still symmetrical. You can rotate around this point. Cool, eh? Because the space between the roots is all symmetrical. And now let's go sextic. So we will have an x minus 6. So there, that's instructive, isn't it? So we see with this sextic, we have 6 intercepts. We have, count the turning points, 1, 2, 3, 4, 5, as many as the degree minus 1. And let's change some of our roots. So I'm going to get rid of this x minus 2 root and make this x minus 1 a bounce. So now we're no longer symmetrical. We have a bounce there, and then we have 5 more roots. And now let's get rid of these 2 roots, the x minus 3 and the x minus 4. And let's make the x minus 5 a drag. Okay? So now we see the types of roots that we can have here. Let's also change our leading coefficient. Right now, our end behavior is as x goes to positive infinity, y goes to positive infinity, and as x goes to negative infinity, y goes to positive infinity. Okay, but let's change our behavior there by making that negative, and let's make this point 0.01. So we have a very, or let's make 0.1 there. So we have now a very condensed function. You see it's, because it's sextic, it still just dives down. It's just so powerful, the effect of those variables. But now we can see the 3 types of roots really nicely. Here's a bounce. Here's a drag. You see it comes up, it drags along the axis before picking up again. There's our local maximum there, which Desmos locates for us at 5.7, and there's a cut. So we see the 3 different types of roots there. Okay, continuing on. Questions about any of this stuff, do come find me. Okay. So let's keep going. So when we're talking about end behaviors, we have 2 different types of functions. We have even functions and odd functions, and these are determined by their degree. So linear functions are odd, quadratic functions are even, and so on. Okay? Even functions have the same end behavior in both directions. So as x goes towards positive infinity, and this is the way we notate these. As x approaches positive infinity, y approaches positive infinity, and as x approaches negative infinity, y approaches positive infinity. Okay, so as x gets very, very negative here, if our leading coefficient is positive, it goes up. So we can do this dance. Okay, if our leading coefficient is negative, then we do this dance and we go down. Okay, so if we're negative here, then we would just have the other. As x goes to positive infinity, the value of the function, f of x, goes to negative infinity. And as x goes to negative infinity, well, then the value of the function, f of x, also goes to negative infinity. And it's just that simple to notate. All right. With our odd functions, on the other hand, like our linear functions, these are all with positive coefficients, or our cubics or something that have this type of shape. I violated vertical line test there. It shouldn't loop back. We have opposite behavior, where we have to do this dance or this dance to describe their end behaviors. So when the coefficient is positive, we have as x goes to positive infinity, we're going up here. So as x goes to positive infinity, y goes to positive infinity, and as x goes to negative infinity, well, we can see as x goes to negative infinity, y is going to negative infinity also. All right. And then here with negative leading coefficient, it's reflected. So here is y is equal to negative x, and that's a good model for you to think about. As x goes to positive infinity, f of x goes to negative infinity, and as x negative, y, f of x or y, doesn't matter. Let's just keep it consistent for that line, though. Okay, so that describes our behavior as we go that way. Now, what's the difference between talking about y and f of x? There isn't a difference. Just keep it consistent. Okay, and just for your purposes. All right, so let's talk about these examples. Here, I can identify that I have 1, 2, 3, 4 turning points. So I'm at least degree 5. I am quintic. And I have 1, 2, 3, 4, 5 roots, which are all cuts. So again, I'm quintic. And my end behavior is over here. As x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to negative infinity. So that tells me that I am negative. All right. And I could say that this is Q2, this is quadrant 2 to quadrant 4. But don't be lazy. Write out your end behaviors this way, please. Okay. Next, this one, I can see that I have 1, 2, 3 local maxima or minima, and 1, 2, 3, 4 cut roots. So I am an x to the 4. I am quartic. And my leading coefficient is positive because I have this end behavior. Here, I have 1, 2 local maximum or minima. So am I cubic? No, I'm not cubic. I have 1, 2, 3 roots, which does correspond with cubic, but that one's a drag root. So that one I know is like a triple root. So I have 1, 2, 3, 4, 5. I am an x to the 5 here. I am quintic with a positive leading coefficient because of, and I know that because of my end behavior is doing this dance. Here, I have a bounce root, so that's like worth 2, that bounce. This one's worth 3, and then here's a cut, so that's worth 1. So altogether, I am sextic. And I know that I'm sextic because of the nature of those roots. I only have 1, 2, 3 local maxima or minima, and I can have as many as 5 with a sextic. I don't have that many, but I recognize that I have a drag root there and a bounce root there, and the bounce root is worth 2 factors and the drag root is worth 3, so I am sextic. My coefficient is minus because I have this end behavior. So again, describe your behavior this way: as x goes to positive infinity, f of x goes to negative infinity, and so as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to negative infinity as well. We can also determine our end behavior just by looking at equations. So this one I know is going to have this end behavior because we are even and we have a negative coefficient and we are quartic. And then here we're quintic. We have a positive coefficient, so our end behavior will be like this, and you notate it properly. You say things like as x. You can write it out with words if you want, but you don't have to. You can just write the as x arrow positive infinity. Yeah. And again, same idea here. Here we are quartic. We have a positive leading coefficient, so we're some type of behavior like this. And then this one, we are cubic. We're negative, so our end behavior, it's going to look something like that. Carrying on. Okay, so turning points have to do with like, well, a quadratic has a single turning point, and it's called the vertex. But a cubic or higher order might have local maxima or minima. These are the greatest, local maximums are the greatest y values over a certain interval. Doesn't matter how wide that interval is. It can be very narrow, but so long as it like comes up, turns, and goes down again. Another way of thinking about that is the slope there is 0. Like you could rest a tray on that or something. Like the slope is 0. at those points, then there are local maxima or local minima. Here, this is a local minima because it's the least y value for some interval. It's not an absolute minimum because this function does go off to negative infinity in that way and positive infinity in this way. So this is not an absolute maximum, but it's a local maximum. So we can see those here, like -1, 4 and 1, -4 are a local max and a local minimum. And that's how we talk about those. So any questions about this stuff, you find me in class, you find me at lunch, you email me and ask me questions. I love to talk about this stuff. Try these practice problems, try your Delta Math, and I look forward to supporting you on all of these topics. Bye for now, everyone. Thanks so much for showing up for your math learning.